Assalamualaikum warahmatullah. So now we are moved to topic hydrodynamics in the fluid flow. So this is the list of references. So now we look into the overview of this chapter. We have 3.1.7 for flow measurement. So this is the learning outcome for this subtopic. Alright. So flow measurement are required for many reasons. Example, to monitor the fluid system, to ensure the adequacy of water distribution network. So meaning that we need to calculate the velocity, the flow rate for each of the pipe networks, just to ensure that the water that flow into this system is adequate enough for the daily uses. So some instruments give direct reading, while others, such as other parameters, that need to be converted to the flow parameters using formula or empirical correlation curve. So ada parameters yang kita dapat direct guna specific instrument, specific device. But then we also need to convert. Okay, so for example, flow rate Q. Okay, Q is equal to VA. Okay, so Q, flow rate, equal to AV. So we need to know the area of the pipe, the diameter, okay, or the radius, right? And then by using device, we can determine the velocity. But then velocity is in meter per second. So to identify the flow rate Q, so we need to use the formula A times with the velocity, right? So this is what does it mean by parameters of Q can be determined by using formula or empirical correlation, meaning that when we have the graph, okay, so maybe Q to the versus like A, so we have a graph. So by using A at this point, so what is the Q? So that is by using empirical correlation curve. And then factors in selecting the flow measurement instruments, we have the range of the fluid flow, and then we have the accuracy required, okay, and then the energy losses, and then the correction, and for the determine the cost. So this is the flow measurement device. So we have the Pitot tube, ventrimeter, orifice, small orifice, large orifice, and the notch or weirs. So first, let's look into the Pitot tube. So this is the Pitot tube in a L shape. Okay, so we have this Pitot tube being inserted into the water, and then this is the water level. So there are some meniscus, okay, there are some capillary, okay, at the H depth. Okay, so now the Pitot tube is being inserted from water level to the Z depth. Okay, so when we have the velocity at a point A, okay, and then a particle moving from A to B will be brought to rest. So meaning that the A to B is the same velocity, and then when the molecules at point B will have the U naught and P naught. So now let's look into how to calculate the velocity at point A. So when we have the head loss of A equal to head loss at B, So we are using the Bernoulli equation. So by putting the P pressure at A over rho G plus U at A over 2G plus ZA equal to P naught, that is at B, over rho G plus U naught at B over 2G plus ZB. So ZA is equal to ZB. So means that we can just eliminate the Z. Okay, ZA minus ZB. So that's why when we simplify this equation, we just remain the P over 2G, P over rho G plus U square over 2G. Alright, since that U naught is equal to 0, so therefore, we can eliminate this equal to 0. So therefore, we have P naught must be larger than the pressure at A. And then we have the pressure over 2G equal to Z P naught over 2G rho G plus H head loss plus the Z, the depth. And then by substituting the U square over 2G, okay, U square over 2G here, and then we move the P to the right side, so we can write it down like this, must equal to height H. Okay, so therefore the velocity at A is equal to the velocity theory. So what is velocity theory? So by having the formula V theory equal to square root of 2GH. Therefore, when we put the C for Manning equation coefficient, so we have the real velocity equal to the C times the V theory. So therefore, by substituting the V theory 2GH, so we have V equal to Manning equation, Manning coefficient times the square root of 2GH. So that is the velocity at A. That is for theory. So having the stagnation pressure, the sum of the static and dynamic pressure. So what does it mean by stagnation pressure? It is the sum of the static and dynamic pressure. So it represents the pressure at a point where the fluid is brought to a complete stop eccentrically. So we have this equation, P stagnation, pressure stagnation equal to the P plus rho V square over 2. So we rearrange of this formula. So by putting the V to the left side, then equal to P 2, okay, so 2, okay, times P stagnant minus P over rho, and then square here we have the square root. So therefore, this is the diagram of the stagnation pressure hole. We have the hole at the very okay, so this is the static pressure holes. Okay, so by having this Pitot tube insert into the water level, so we have the piezometer here. So the height of the piezometer must be lower than the depth of the Pitot tube, because the velocity is moving first to the piezometer, and then it being inserted to the Pitot tube. So this is the static pressure P. Okay, and then the difference of the level between the piezometer and Pitot tube we calculate by using the V square over 2G. Okay, so this is called the proportional to dynamic pressure. And then stagnation point can be calculated. Okay, so this point can be calculated by using V equal to P stat over minus P over rho. So this is called the static, dynamic, and stagnant pressures measured using the piezometer tubes. So now let's look into example. So we have the piezometer and pitot tube are tapped into a horizontal water pipe as shown in figure 5.41. So to measure the static and stagnation pressures, so for the indicated water column height, determine the velocity at the center of the pipe. So you need to determine the V1. Okay, so how to do this? First we have the static and stagnation pressures in horizontal pipe, and then by assuming the flow is steady and incompressible, and we have point 1 and 2 close enough together that irreversible energy loss between these 2 points is negligible. Thus we can use the Bernoulli equation. Okay, so noting that point 2 is a stagnation. Okay, at point 2, where is the point 2? So here 2, it is a stagnation point. Thus the V2 is equal to 0, right? So previously we have example that U0 is velocity at the stagnation point is 0, and then Z1 is equal to Z2, right? Okay, Z1 is equal to Z2. So because it being insert at the same depth, right? So Z1, okay, is equal to Z2. Alright, and then the application of Bernoulli equation between point 1 and 2 given. So we have this equation for point 1 and then equal to 4.2. Okay, so Z1 can be eliminated because it is the same depth. Okay, so by substituting this, we simplify into this equation, and then we substitute the pressure 1 and 2. Okay, so we can have this pressure 1 and okay, by having point H1, okay, you just putting the H13, H27 and H312 into this formula. Okay, so H1 and H2, so you just plus, and then you plus this and minus, and then rho g minus rho g over rho g, so you just eliminate this, and then you get your H3. Alright, so when solving for V1 and substitute into this equation the theoretical value for the velocity, so 2g is the gravity and h is 0.12 from the equation above. So we have 1.53 meter per second for the velocity in the tube, in the pipe. Okay, so note that to determine the flow velocity, all we need is to measure the height of the excess fluid column in the. So this example, we have the Pitot tube. Okay, this is the Pitot tube combined with mercury. So this is a mercury manometer connect to a pipeline. So this is the pipelines to measure the flow parameters in the pipe. So the pipeline is 50.8 centimeter diameter. Alright, so you need to calculate the velocity and flow rate at point 1. So we need to calculate the V1 here. So by having the manometer, we must divide into 2 limb. Okay, for the left limb, we have left limb here. Okay, left and right. Okay, we have the Px equal to P2 plus rho g. So rho is 1000, and then gravity is 9.81. So this is the rho g times with h. So h is Okay, the total height of 50.8 centimeter plus 25.4. So we just 50.8 plus 25.4 centimeter. So you have 76.2 centimeter. So we need to convert into meter because gravity is in meter per second. So for the right limb, so we have Px equal to P1 plus the rho g here, the water, times with this one, the height is 50.8 centimeter. So this one convert to meter. And then the rho for mercury. So rho for mercury is so what is the value times with the gravity. So we have 1,33416 times with the depth of the mercury, 25.4 centimeter. Convert to meter. Alright, so now we have Px equal to Px. So P2 for the left limb, P2, okay, remain, and then P1 for the right limb, remain. Okay, so you solve this value. So you have P1, P2 minus P1, so here equal to 31.396 kilopascal. Okay, so then point 2 equal to stagnation point. Right, so point 2, where is the point 2? So this one is, we know when we have stagnation point is velocity at point 2 is 0. Okay, and then where's that point 2 is 0? So H1 equal to H2. So P1 over gamma plus the V square over 2G plus Z. So the same thing for left limb. And then as we know that when the pitot and the manometer being inserted at the same depth, okay, so meaning that Z1 is equal to Z2. Okay, so we can eliminate the Z1 minus Z2. And then we know that the velocity 2 is 0, so we can eliminate this. And then the remaining parameters is P1 over gamma plus, okay, this one, and then plus equal to P2 over gamma. So therefore, we have to rearrange of this formula, and then you calculate P2 minus P1. So by solving all the equation, all the parameters, all the value into the equation, so we have V1 is 7.924 meter per second. And then by having the Q equal to AV, so V is obtained from previous from the above, and then the A is the pi d square over 4. So we have given the diameter in the question, so it's 50.8 centimeter. So you just put the value and then you solve for area, so you have your flow rate. So that's all for example 2. Now we move to the venturimeter. So venturimeter consists of short converging conical tube leading to cylindrical portion. So we have short conical tube. So this is the conical tube leading to the cylinder portion here, and then this is called the throat. Okay, a smaller diameter of pipeline, which is followed by diverging section. So it may be continue, followed by the diverging section, and then in which the diameter increase again to the main pipeline. So converging section will increase again to the main pipeline. So water, fluid may flow from the section 1. So this is the section 1 here, and then section 1. So here is section 1 with the A1, pressure 1 and V1, and then it may flow into this section 2. Section 2 with A2, P2 and velocity 2. So the depth from section 1 to the datum is Z1, and from section 2 to the datum is Z2. So the pressure difference to determine the volume, flow rate, velocity can be determined by U-tube manometer. So we have this U-tube manometer, and then to obtain the pressure by applying the Bernoulli equation between section 1 and the throat at section 2. So the throat is at the section 2. So this is the throat. And then this is the divergence. Divergence to the main pipeline. Diverging section increase again to the main pipeline. By applying the Bernoulli equation to 1 and 2, so H1 equal to H2. So we have the Bernoulli equation H1, Bernoulli equation at section 1 equal to Bernoulli equation at section 2. So therefore, due to the V2 minus V1, so V2 minus V1 equal to 2G, so we have the pressure difference of P1 minus P2 over 2G over rho G plus Z1 minus Z2. So Z1 is the difference of section 1 to the datum, minus Z2 is the section 1, section 2 to the datum. So then we can calculate the flow rate by having Q1 equal to Q2. So Q1, definitely the area is different, because area 2 is at the throat. So we can solve for velocity 2. So pressure difference between 1 and 2, considering pressure are level, XX must be the same in the both limb. So Px equal to Px, so it is the same at the both limb. And then we use formula pressure plus rho G, so for left limb and then for the right limb. So we can calculate the pressure difference, P1 minus P2 equal to negative rho GH plus P manometer times GH. So V1 we can substitute into this 2GH, and then we just solve all these values. So P man is the manometer density, rho in the manometer. So if in the manometer we have mercury, so we need to use the rho for mercury. And then the gravity is 9.81, and then the manometer level H, density for water, and then the cross section area and the sectional drop, at